Yeah, good morning all. Now I am going to explain about some more problems on transformers. Okay, first question. In an ideal transformer, the impedance can be transferred from one side to another side. Remember, in case of only ideal transformer, okay, the impedance is directly proportional to square of its turns. The impedance is directly proportional to square of its turns ratio. Turns ratio is nothing but n1 by n2 whole square. Okay, that is impedance is directly proportional to turns ratio. Turns ratio is equals to n1 by n2, that is equals to e1 by e2, that is equals to i2 by i1. Okay, whereas transformation ratio is e2 by e1, that is equals to n2 by n1, that is equals to i1 by i2. Reciprocal. Transformation ratio and turns ratio both are reciprocal to each other. That means 14th question answer is A. Next, distribution transformers are designed to have: option A, core loss is greater than full load ohmic loss; option B, core loss is less than ohmic loss; option C, core loss is equals to ohmic loss; option D, core loss is negligible as compared to ohmic loss. In case of distribution transformer, while designing, core losses or iron losses is equals to 2 times of copper losses. That means copper losses are more than iron losses in case of distribution transformer. In case of power transformer, iron losses is equals to copper losses while designing. That means from the given options, PC is less than PO suffix H. That means second option is correct. Next, a transformer has sometimes two or more ratings depending upon the, okay, see here, practically the transformer ratings are designed. For example, let us consider 10 by 16 MVA. Okay, 10, that means that transformer can be used for 10 MVA rating as well as 16 MVA rating. Okay, the rating will be improved by using cooling technique. Okay, that means 16th question answer is first one. Okay, cooling will always improve the rating of the transformer. Next, in transformer, exciting current is made up of with two components, namely magnetizing component of current and core loss current IC with negligible leakage impedance drop. Okay, that means under no load condition, no load current is divided into magnetizing component of current, iron loss component of current, or core loss component of current. Okay, now you can observe this is the phasor diagram under no load condition. Okay, see here flux, here I mu or Im is nothing but magnetizing component of current from this phasor diagram, which is required to produce a working flux in the transformer core. Okay, V1 is the applied voltage. Okay, now see here from this phasor diagram, V1 is leading or current is lagging voltage by 90 degrees. Okay, IC is core loss component of current. That means the phase angle between core loss component of current, that is IC, sometimes it may be represented by I suffix W. Okay, here magnetizing component of current Im or sometimes some textbooks it is represented by I mu. Now see here the phase angle between IC and Im is 90 degrees. Okay, now from the given options, both magnetizing current and core loss current lags supply voltage by 90 degrees. That is not correct, right? See the phasor diagram. From this phasor diagram, supply voltage is nothing but V1 and core loss component of current IC both are in phase. Okay, whereas magnetizing component of current and applied voltage displaced by 90 degrees. That means IC lags voltage by 90 degrees. That means first option is not correct. Next, second option, both Im and IC are in phase with V1. That is not correct. Next, third option, Im lags V1 by 90 degrees, right? First point is correct, and IC is in phase with V1. That means third option is correct. Next, a transformer at no load is excited at rated voltage. Now a cut is made in the transformer yoke, thus creating a smaller air gap with this transformer core flux. Okay, see here, transformer is a constant flux device. Okay, if we increase the air gap also, there is no change in flux. Why? Because here V by F ratio is constant. That means flux remain constant, but in any machine when air gap is increases, the reluctance of the magnetic circuit is also increases. Okay, when air gap increases, reluctance is increases. When reluctance is increases means magnetizing component of current is also increases, then power factor will be reduces. Okay, that means when air gap increases means indirectly flux decreases for remaining machines, but except transformer is a constant flux device. Okay, that means see here from the given options, flux remains constant and Im is increases, right? Okay, now see here, transformer doesn't have an air gap, whereas induction motor is having some air gap in the core. Because of that one, no load current of induction motor is very high. Here in case of transformer, no load current is around 2 to 6% only. In case of induction motor, 30 to 40% of no load current. Okay, that means 18th one answer is B. Next, if the secondary winding of the ideal transformer shown in the circuit has 40 turns, the number of turns in the primary winding for maximum power transfer to the 2 ohm resistor will be. Now see here, when he is given ideal transformer means input power should be is equals to output power, then copper losses also should be equal. Okay, that means why? Because here resistance R is given, right? That means I can equate input copper losses should be is equals to output copper losses. Okay, that is I1 square R1 is equals to I2 square R2. From that equation, I1 by I2 whole square is equals to R2 by R1, right? Secondary resistance is given as, how much is given? Secondary resistance is 2 ohm. That is 2 by primary resistance is 8 ohms, and secondary turns he is given, that is 40 ohm, right? That means now see here, already we know that transformation ratio K is equals to N2 by N1, that is equals to E2 by E1, that is equals to I1 by I2. Okay, that means in place of I1 by I2 I can substitute N2 by N1. Why? Because in the given data he is given number of turns. That means N2 by N1 whole square is equals to 2 by 8. Then N2 by N1 is equals to 1 by 4. That is N2 by N1 is equals to under root 1 by 4. That is N2 is equals to N1 by 2, right? Then N1 is equals to 2 into N2, right? Sorry, here it is 80 ohm is mistake, that is 80 turns. That means 19th answer will be, where is 80 turns? C is correct. Next, from the figure, in a single phase transformer, polarities of a transformer A and B at any instant are shown in figure. Okay, for this question direct answer will be C, that is C is negative and D is positive, flux is counterclockwise. Next, okay, in an oil filled transformer, the oil provide, okay, oil serves two purposes, oil provide cooling as well as it provide insulation. Okay, that means from the given question the answer is it provide cooling and insulation, right? That means 21st answer is C. Next, transformer cores are laminated. Okay, lamination technique is used to reduce the eddy current loss. Okay, if in the problem is given silicon steel, by using silicon steel we can reduce hysteresis loss. Why? Because silicon steel is having less value of hysteresis coefficient. Okay, the hysteresis loss formula will be omega suffix h is equals to neta b maximum whole power x into f into v. Okay, x is nothing but hysteresis coefficient, that value is varies from 1.5 to 2.6. Okay, whereas silicon steel x value is 1.6, lower side, right? Hence hysteresis losses will be less when we use silicon steel material. Okay, that means for this question, transformer core or lamination technique is used to reduce eddy currents. That means 22nd answer is A. Next, 23rd question, CRGO laminations in a transformer are used to minimize option A eddy current, option B hysteresis loss, option C both hysteresis loss and eddy current loss, option D ohmic losses. See here CRGO and cold rolled grain orientation, that is also silicon steel. Okay, by using CRGO steel only, weight cast size of transformer is very less. Why? Because CRGO steel is having high flux density, B maximum value is varies from 1.6 to 2 for CRGO. That means by using CRGO we can reduce hysteresis loss. Okay, by using lamination technique we can reduce eddy current. That means here both hysteresis and eddy current losses are reduced. That means 23rd answer is C. Next, 24th one. In case of power transformer, the no load current in terms of rated current is, okay, in case of transformers, no load current is approximately 2 to 6% only. That is, second bit is correct. Next, if a transformer primary is energized from a square wave voltage source, then its output voltage will be, okay, when transformer primary is energized with a square wave, the output voltage is pulse waveform. Next, the primary voltage of a 220 volts, 220 volts by 6 volts, that is E1 by E2 rating, 50 Hz transformer is connected to 110 volts, 60 Hz source. The secondary output voltage will be, that means here we need to maintain voltage ratio should be constant. Now see here, first case the voltage rating is, I am assuming E1 by E2. Second case voltage rating is E1 dash by E2 dash. Then E2 dash is equals to E1 dash into E2 by E1, right? That is 110 into 6 by 220. That value is 3 volts. Okay, that answer is 3 volts. Okay, next. The no load current in a transformer lags the applied voltage by. Now see here, already we saw the phasor diagram in starting question itself. That means either 16th or 15th. See here, this is the no load phasor diagram, right? Here Im is the magnetizing component of current, Ic is the core loss component of current. The vector sum of Im and Ic is nothing but no load current. Okay, that value, that means now see here, if I draw this one, see here, that means the sum will be is on from where it is varies from 0 to 90 degrees. Okay, the no load power factor angle will be approximately around 70 to 80 degrees. Okay, that means from the given options about 75 degrees, right? That is no load power factor angle will be about 75 degrees. Approximately that value is varies between 70 degrees to 80 degrees. When power factor angle is increases, power factor is reduces. Transformer under no load condition, it is having very less power factor, approximately 0.2 lagging. Next, a transformer has N1 and N2 turns in primary and secondary windings respectively. Its secondary reactance when referred to primary is, okay, remember one point, when transformer winding resistance when transferred from secondary to primary, okay, that means secondary resistance is R2, right? Okay, that is when it is transferred to primary, R2 is replaced by R2 dash. See here. Okay, second, assume first of all secondary primary winding resistance is R1, secondary winding resistance is R2. Okay, when R2 is transferred from secondary to primary from first figure, that means R2 is replaced by R2 dash. Why? Because that is changing resistance. Okay, then total resistance referred to primary side is represented by R suffix 01. Okay, that is equals to R1 plus R2 dash. R2 dash is equals to R2 by K square, where K is equals to turns ratio. That value will be N2 by N1, that is equals to E2 by E1, that is equals to V2 by V1, that is equals to I1 by I2. Okay, that means you can, that means when resistance is transferred from secondary to primary, R2 dash is replaced by R2 by K square. K is nothing but N2 by N1 whole square, right? If it comes to numerator, N1 by N2 whole square, right? That is R2 dash value is equals to R2 into N1 by N2 whole square. Okay, similarly when resistance is transferred from primary to secondary, then that is R1 is replaced with R1 dash from second figure. That is when total resistance is referred to secondary side is R2 plus R1 dash. Okay, here R1 dash will be K square into R1. Okay, now K value already we know, right? That means here also R1 dash, K is nothing but N2 by N1. That means square of transformation ratio are reciprocal to the turns ratio, right? Now see here from the given options, same reactance also same as resistance. R is replaced by inductive reactance X. Now see here, secondary winding, if it's secondary winding reactance, that means when referred to primary, that means X2 is transferred to primary side, that is replaced by X2 dash, right? x2 dash is equals to x2 by k square, that is x2 into n1 by n2 whole square, right? From the given options, what is the answer? C is correct. Next, 29th question. A 400 by 200 volts transformer has total resistance of 0.02 per unit on its LV side. This resistance when referred to HV side would be, remember this point, just underline that resistance of 0.02 per unit. Okay, per unit resistance will be equal on primary side as well as secondary side. That means first option is correct. Next, the leakage flux in a transformer depends upon, leakage flux always depends upon load current. That means next the question answer is C is correct. Okay, thank you all. Remaining we will see in next class. Thank you.